You've seen how powerful the task parallel library is, as well as the parallel operations that it provides. With these advanced topics that we've covered throughout this module, you now have a better understanding of how to build some powerful and better performing applications. You started off learning about sharing variables between parallel operations. This showed you that it's extremely important to be cautious when introducing a lock and a lock object. Sharing variables is often needed, but without the understanding of the problem a lock can introduce, it may become rather difficult. Now you know that a lock should only do the very bare minimum, and most of the work should be performed outside of the lock statement. This will ensure that your code runs as fast as possible. Running too much code inside a locked context may in fact make your application perform as bad as an application without parallel principles. Once you understood how to share variables, we looked at performing atomic operations in a thread-safe manner. This together with the interlocked class. Of course, this requires that you work with integers, which in our case resulted in a bit of data loss, as we had to cast the decimal to an integer. The interlocked class is not for every use case. However, if you can, I would strongly suggest that you use this instead of a lock object. You also learned about deadlocking, why that occurs in parallel operations, and now you know that it happens when you have a nested lock. It's a bit trickier to get a deadlock in comparison to when using async and await. Knowing why it happens and how to prevent that will allow you to structure your code to avoid this. A good rule of thumb is to avoid sharing lock objects. You then learned how to cancel a parallel operation. If you request a cancellation, no further operations will be started, and an operation canceled exception will be thrown. This is a little bit different from how stop and break works, as those had to be manually handled. With the understanding of the task parallel library, it shouldn't come as a surprise that a task won't start if you pass a cancellation token marked as canceled. This is exactly what's happening internally when using parallel for each, and invoke. Remember though, it won't cease the current executions. It just won't start new ones. If you have to roll back data, you'd obviously have to handle that on your own. Finally, we talked about thread local and async local variables. They're completely different and do behave rather differently from each other. We saw that thread local variables may flow across different tasks because internally the task reuses threads. We also saw that async local variables creates a copy per asynchronous context, if you write to it, that is. You can set the async local value and it flows to subsequent calls. But if those asynchronous methods change that variable, a local copy will be created for that context. Both the thread local and async local types are extremely powerful and useful. It's important to understand how they work and not be surprised by the fact that threads are shared between different tasks. With all of this covered, you're definitely ready to tackle parallel programming and build more powerful and better performing applications. In the next module, we are going to explore the last piece of the task parallel library, which is parallel link. If you already use LINQ in your applications to process collections of data, applying the parallel principles to that may result in a much faster application. So continue to the next and final module to learn about that.